Hello students, welcome to the lecture 3 from the chapter 5, that is features of Lpc2148 IC. We are already familiar with the other features of Lpc2148. We have seen many things about the 2148. So let us explore some additional things about this IC. So at the end of this lecture, you will be able to understand basic features of Lpc2148, peripherals available in 2148, and along with that you will also understand the applications of 2148. Okay, so just revision of some things and then we will go to the next part. It is integrated circuit manufactured by NXP, formerly known as Philips. It is ARM7 TDMI-S based chip. That ARM7 TDMI acronym I will tell you, it is ARM, means Advanced Risk Machine. 7 version there. T is thumb, it supports thumb mode, debugger, it supports online debugger. M is the multiplier unit, it is having its own multiplier inside it, and I stands for in system programming. S is synthesizable, it is having a synthesizable code there. So this is about the ARM7 TDMI-S architecture, which is supported by Lpc2148. It is a quad package, that is, it is having 4 sides where you are having the pins available there. It is assembly chip, surface mounting device. Its package is LQFP64. It means it is having 64 pins available there. On every side it will have 16 pins available there. So the size of the IC is 10 by 10 by 1.4 mm, means it's highly 1 centimeter by 1 centimeter chip. So you can see that this is a very high, it is having lots of features inside it, but the size is very small, it is very tiny. 1 by 1 centimeter chip is available there, and it works only on 3.3 volt. So that is another biggest advantage of Lpc2148. So highlighted features, it is based on 32-bit ARM7 TDMI-S CPU. It has embedded high-speed flash memory. It is having 128-bit wide memory interface, tiny size and low power consumption. I will also give you some applications there. It is used for communication gateways, for protocol converters it is used for soft modems, voice recognition, low-end imaging, industrial control, and for medical systems. So these are wide variety of applications where Lpc2148 IC can be used. So for these various applications you can use this IC. This is a very powerful IC. You can run many algorithms there for this IC. So this is the block diagram. System part of this ARM7 TDMI-S based IC Lpc2148 we have seen there. Then we have seen the memory map also in the previous lecture. So we will start with the next one, memory accelerator module or MAM module. Here you can see that this is the bus interface available inside the IC, and in this bus interface what you are having is so this is the bus interface available for the ARM IC. Okay, and so this is local bus, means it is going inside the IC. So here you can see that this is the actual part of the IC available there, Lpc2148, and this is your flash memory bank where your program is stored. Okay, so this is the different parts there, and this is flash memory. Of course this is also the total part of the IC is like this, but still your flash memory consisting of different the code of the that IC is present in the flash memory. So normally what happens, this flash memory contents will go inside the memory, or those are decoded by the by Lpc2148 CPU, and then it will execute it. Whereas in case of memory accelerator module, it is using slightly different thing. It is using buffers. So these buffers are used to fetch the data ahead of the time. So before it is actually given for decoding, the data is actually fetched ahead of the time, means prior to the execution the data is available in the buffers. Okay, and then it is fetched to the in the system. How it is useful, we will see here. It is actually increasing the speed of the program execution. Why? Because your data or your instructions are present ahead of the time inside the IC. Using the buffer, you are actually fetching the instructions ahead of the time. Not only instructions, you are also fetching data from the memory ahead of the time. It fetches instructions oblique data from memory ahead of the time, that is before execution they are ready to be used in the program. Memory accelerator module. To have the next arm instruction that will be needed in its latches in time to prevent CPU fetch stalls. Stalls means the CPU is waiting for that instruction to be fetched. So instead of that, it will fetch the data ahead of the time. It uses three different buffers. One is prefetch buffer, second is branch trail buffer, and third is data buffer. So you can see that it is working on three different buffers, and every buffer is 128-bit wide. All the three buffers are 128-bit wide. And what is the length of a single data or single instruction in case of Lpc2148? It is 32-bit. So using 128-bit buffer, you are getting actually 128 divided by 32. It comes out to be 4. Am I right? So you are fetching 4 instructions before time. You are fetching 4 data items ahead of the time. Okay, so where it is stored, these are stored in the buffers. 3 different types of buffers are present there. Prefetch buffer, which is used for normal program execution. Branch trail buffer, that is used specifically in case of branch instruction, where you want to prefetch those instructions which may execute when the branch instruction is executed. Those are again stored in the buffer. And the last one is the data. It can also fetch data ahead of the time. Okay, so the only reason you are using the memory accelerator module is to speed up the program execution. So for that you are using buffers and you are fetching the data ahead of the times. Okay, so prefetch and branch trail buffers each include 4 32-bit ARM instructions or 8 16-bit thumb instructions, and memory accelerator module attempts to have the next ARM instruction that will be needed in its latches in time to prevent CPU fetch stalls. Okay, so this is about the memory accelerator module. Then we are going to study the next important part of the system block of Lpc2148, and that is the clock signal. Okay, so you are already familiar with the clock signal of 8051. Same thing I am going to repeat here. In case of Lpc2148 also, as usual, 2 options are available. One is you can use external clock signal which is going to drive Lpc2148. So you can give directly one clock signal from one clock source. You can take it and you can give it to the 2148. That is the external clock signal. And the second one is you don't need the clock signal, that is you don't need function generator or any other thing. You can use its own internal oscillator and in that case you are using crystal to generate that frequency. So crystal is the external part which is connected to the LPC2148 internal clock circuit, and it will execute it. It is shown in the next slide. Okay, it is shown in this side. Here you can see that I will show you this thing. This is the clock signal. Clock signal means you can say that it is your function generator which is going to generate the clock signal, and that function generator output is connected to the LPC2148 at crystal 1, and crystal 2 is kept open, or it can give you the signal outside. Like that it will work. This is the one way, first way external signal is used. Or you can generate the internal clock signal by other method also. And the second method is connect crystal to the LPC2148 at the points XTAL1 and XTAL2. So when you connect the crystal at these 2 points, internal clock oscillator will generate the clock signal using the crystal, and crystal will decide the frequency. Here the clock signal generator will decide the frequency. So this will decide the frequency. Here crystal will decide the frequency. Okay, and the third one is actually the equivalent circuit of crystal is shown here. This is just for your information given. Okay, then before going to the details of this, let us see what are the clock frequency ranges available there. Okay, in case of LPC2148, it is using internal PLL. PL is nothing but phase locked loop which is available inside the 2148. So if you are using PLL or in system programming ISP, it can generate the frequency from 10 to 25 megahertz. The frequency is restricted from 10 megahertz to 25. Means you have to give only 10 to 25 megahertz if you are going to use PLL there. Okay, that may be your crystal or that may be your external clock signal. Okay, so it is not saying that what is the frequency. If you use PLL or ISP, it will be always 10 to 25 megahertz you have to provide there. Either it may be crystal or it may be external clock signal. Okay, but when no PLL or ISP is used, what will happen? The crystal, if no PLL or no ISP is used, in that case, if you are using one second way, that is crystal is used, then the frequency range is 1 to 30 megahertz. You can use the crystal of 1 megahertz, or maximum you can use the crystal of 30 megahertz. Okay, similarly, if you are not using the crystal, it means you are using external clock signal, then the frequency range varies from 1 megahertz to 50 megahertz. So remember, these are the 3 different clock frequency ranges available there: 10 to 25 megahertz, 1 to 30 megahertz, or 1 to 50 megahertz is available there. Okay, the same thing is given here using this oscillator F oscillation selection algorithm flowchart. So in this flowchart you can see that this is the F oscillation selection process. So when you are going through this, it will check first whether it is on-chip PLL is used or not. If the on-chip PLL is used, then the frequency range is restricted from 10 megahertz to 25 megahertz. As we have discussed previously, it is 10 megahertz to 25 megahertz. If PLL is not used, then it will verify whether it is ISP is used. If ISP is used, then again the frequency range is limited to 10 megahertz to 25 megahertz. If ISP is not used, then it will go for 2 different options. Either you will use the external clock signal, external crystal. When you use external crystal, the frequency range is restricted from 1 megahertz to 30 megahertz. It means it is expanding the frequency. And finally, if you are using external clock signal as the input to the LPC2148, in that case the frequency is 1 megahertz to 50 megahertz. So this is about the F oscillation selection algorithm, which is used to generate the clock signal for LPC2148. So remember, you should be able to explain this flow chart correctly, so that it will give you how the signal is generated there. Remember, PLL is totally different aspect of 2148, and we are going to study it in detail afterwards. Okay, so with that we will go to the next point. Power control registers. So you are familiar with the power control concept of the controller. Power control is actually saving the power of the controller. So when you want to save the power for the microcontroller, there are different variety of options available there, like power down mode, idle mode. Okay, so how the power control is done in case of LPC2148 is given here. So it is basically working with two registers. One is PCON and second is PCON P. So PCON is a power control register for basically, so here you can see that PCON is a power control register. This register contains control bits that enable the two reduced to power operating modes. Means for idle mode and power down mode you have to use PCON register. And the second register is PCON P. P stands for peripherals. So it's a power control for peripheral registers. This register contains control bits that enable or disable individual peripheral functions. We have seen the list of the peripherals for the LPC2148, like it contains ADC, DAC, I2C module, SPI module, UART, then it contains USB. So all these modules can be turned on or turned off individually, and that is done by PCON P register, power control for peripheral registers. If you turn on that particular bit, it will be enabled. If you turned off that particular bit, it is disabled. Means you don't have to completely work with all the peripherals of LPC2148 at a time. You can switch off a particular peripheral at a time so that your power is saved there. Okay, so for that PCON P register is used. Then in case of power control registers, there are two bits are reserved there. One is bit 0. Bit 0 is used for idle mode. In this case, the processor clock is stopped while on-chip peripherals remain active. Means in idle mode, processor clock is stopped and on-chip peripherals are active. Any enabled interrupt from a peripheral or an external interrupt source will cause the processor to resume execution. So if any interrupt occurs, then only the processor will resume its execution. The other one is power down. The oscillator and all on-chip clocks are stopped. A wake-up condition from an external interrupt can cause the oscillator to restart, the PD bit to be cleared, and the processor to resume the execution. Okay, in first case, only the processor clock is stopped and peripherals are working there. Means only processor is not working, but the peripherals are working there. Whereas in case of power down mode, on-chip clock itself, all the clocks are stopped. So no peripheral is working. Only external interrupt can resume the working there. So that is nothing but power down mode. So students, we have seen different aspects related to the system blocks of LPC2148, and this completes the basic features of the LPC2148. We can move forward with different system blocks present in the 2148, and we will study different registers and detailed programming related to other parts or other system blocks of LPC2148. Okay, so I hope you have understood the basic features and applications of LPC2148. So thank you students, thank you one and all.